Congratulations. Over to you, Luca.
So now we have a lot of the pieces to do this transformation where we start from some search problem here. P can be any problem in P. D can be any distribution that is sampleable. And we're going to reduce it to the search version of the bounded halting problem with the uniform distribution. We just saw that this also will reduce to the decision version of bounded halting. So the conclusion will be that if problems that are complete in Levin sense, including bounded halting with a uniform distribution, have an efficient algorithm even just for the yes or no problem, then all problems in NP, all distributions that are sampleable can all be solved with a comparable notion of efficiency, even for the search version. Okay, so let's see how to do this. All right, so we have our starting problem. Say D is sampled by a sampler S. So let's say that S of n samples Dn using M random bits. All right, so now we get an X sampled from this distribution. We want to know if there is a weakness, if so, what it is. We want to map it into something that looks like the bounding halting problem. All right, so here's the idea. So first, suppose that we could compute what is the probability of X under this distribution. So that's actually not a reasonable assumption, but let's make it for now. So in the reduction, let's say that we can compute what is the probability of X under D. And so let's call K kind of the entropy of X, log of 1 over this probability. So in the reduction, we will sample well, we'll pick a hash function H that maps n bits into k bits. A kind of idea would be that here we'll put a machine M, we'll put this as function H, and H of X as before. Because so P is 1 over 2 to the K. Kind of let's ignore rounding to the nearest integer for now. And so this k-bit hash kind of uniquely identifies X among the strings that the sampler generates with probability 1 to the k, because there cannot be more than 2 to the k of them, so they're kind of well identified. However, if we stop here, we're making the task of M really too hard, because now M would have to figure out which of the possible outputs of the sampler have a probability that is 1 to decay. And then among those, find one that has the same hash as the third element of the input. So and also we're assuming that we know the probability of X, which is not really possible. Okay, so then here is the other piece. We're going to pick another hash function. Let's call it G. This one maps M into M minus K. And we're going to add this function as well. So now what does M do? So M will do the following. So M now is given the hash function H of X, but it doesn't see H of X, it just sees some string, let's call it Y. Then there is another hash function G. Maybe I'll call it Z instead of G because I write Y dangerously similarly to G. So what does M do now? Now M is going to guess not just X, but also a possible randomness that the sampler might have used to generate X. So M is going to guess some randomness R. So I'm calling it randomness, but there is no probability here. So just guess, maybe I shouldn't use this word. It will guess some string R of length M, such that G of R is all zeros. So it's just M minus K zeros. And H of G of R is equal to Z, is equal to this piece of the input of M. Then it will call, well, then it will solve the search problem P on G of R. Sorry. This is the sampler and this is G. And this is H. Since I confused myself writing it, I assume you are even more confused than I am. So let's try to decode what this is doing. By the way, this reduction was appeared in a paper by Impagliazzo and Levin, and there were two proofs. One by discussing two different sections. Just by reading those sections, you could tell that one proof was by Levin, and Levin wrote that section, and one proof was by Impagliazzo, and Impagliazzo wrote that section. So what I'm describing here is Levin's proof, which is really nice once all the pieces click. And so once you understand what is going on, it's actually not that difficult. It also is proof that maybe if there is time, I'll tell you a bit about it. It's conceptually simpler, but to get it to work, actually, there is more stuff to do. It's not as clean and elegant as Levin's. All right, so what is the idea here in Levin's proof? So like in all these reductions, what we're trying to do is to find an injective mapping and encoding of X into something that is both decodable and random. And the biggest difficulty in doing this is that X is not uniformly distributed at all. In fact, different X's can have different probabilities. So if you're trying to create some encoding of X where pretty much everything is uniformly distributed, maybe we can afford log n bits of entropy deficiency, but that's the maximum. But in particular, so the way we write down X cannot be longer than the entropy of X, because otherwise, pretty much by definition, we encounter a big entropy deficiency. So if X is something that is generated with probability 1 in 2 to the k, we can only use k bits to write it down. Because if you use more, whatever we are using, it's some bits that are going to occur only with probability 1 over 2 to the k. Because by injectivity, nothing else can produce them except X. X has probability 1 in 2 to the k. So a string X must be written down with not much more than log of 1 over the probability of X many bits. So it's kind of necessary in all those arguments, or so it's not surprising that in all those arguments, the first thing we do when we think about encoding the string is to ask, what is its probability? And the second thing that we do is to budget log of 1 of that probability many bits to write it down. We can also write more things, but all those other things must be also random and independent of X, so that we don't lose any more entropy anywhere else. So so if we want to use a hashing trick, we can pick a hash function that maps to k bits and encode X as h of X. And then we can write the hash function because it's a random hash function, and so it's all extra, kind of extra bits, but we have it's full entropy. There is no entropy loss there. And in a case in which our distribution was flat over a set of size 2 to the k, that was actually all that we needed to do for the decoding. But here, just writing h and h of X is not enough for the decoding, because so this hash function uniquely identifies X among strings that have probability 1 in 2 to the k, but not among all strings. There could be lots of lower probability strings that actually happen to collide in those k bits of hashing. In fact, that's pretty much unavoidable if there are some high probability strings and some low probability strings. The high probability ones will get short hashes, and the low probability ones will create lots of collisions. So that's where this G is coming from. And what is it doing? Well, So let's think about how X was generated. Like X is a possible output of our sampler. Our sampler is taking n bits as input. So for each of the 2 to the m possible settings of the stream of random bits that go into the sampler, there is a possible output. X is coming out with probability 1 in 2 to the k. And so what it means is that so let's collect this thing. So X has probability, we just call K 1 over log of probability of X, so X probability 1 on 2 the K. So S of R so the sampler takes m truly random bits, produces the distribution D. In particular, it produces X with probability 1 in 2 the K. So this means that the number of random strings that produce X as an output, it's 2 to the m minus K. So now to actually identify X uniquely, what we can do is to uniquely identify some R that produces X. Because if that's the situation, there's going to be, at least with constant probability, a unique R among those that produce X, such that if we hash it to m minus k bits, we get all zeros. And so this is the isolation or kind of identification process that takes place here. So this other hash function G is provided to do this isolation of the random seeds for the sampler. And our decoding of X will be to find that R that simultaneously outputs something with the same hash as X. So the output of the sampler given R, if hashed by H, produces H of X. So what we could see here. And in addition, so we expect there to be kind of 2 to the m minus k of them. And in addition, we ask that with a different hash function, the hash of it, it's a sequence of m minus k zeros. So when those two conditions are taken together, over the randomness of G and H, there will be a constant probability that there is a unique way of satisfying solution 1 and 2, and that unique way is to pick out a pre-image of X. So that's our, really, we cannot call it compression anymore because actually it's a super expensive encoding of X. But it's an encoding where like everything is random and X can still be retrieved. And as before, this is succeeding only with constant probability, but no, this is a probability computed with respect to the randomness of G and H, which are controlled by the reduction. So we could just do this several times, like construct the same objects with different choices of G and H, and it just needs to work once because it's a search problem. Just needs to work once so that we get a witness and we have found the witness. In the case in which there is no witness, nothing will work, so we can never make a mistake. In the case in which there is a witness, this only needs to work once. It still doesn't completely describe a reduction because there was still this step in the description of the reduction in which we assume that we knew the probability with which a given element is a sample from our distribution. And that seems to be really important in the argument, because if we allocate too much space for the hash of X, we get large entropy deficiency, our distribution is no more uniform, there is no more a guarantee that the average case algorithm for bonding halting will actually work. But if we allocate too little space, H will not be uniquely defined by all this information. And so it's actually possible that the reduction fails because the machine M will guess the wrong seed, and then instead of X, it will come up. It will not guess X correct. Yeah, so the full reduction is that we sort of be to try this for all K from 1 to 1. So we will sort of guess what is the probability of X, and then run the reduction as if that was the probability of X. Now, this is a bit dangerous because now for the wrong guesses of the probability of X, we are generating instances that have completely wrong distributions. Like when we guess the probability too small, we allocate too much space for h of X. And so we get distributions that are very far from uniform, have a lot of entropy deficiency. And so then our algorithm for bonding halting is not guaranteed to work. If we guess P to be too large, we allocate too little space for h of X. So the reduction can fail in the sense that even if the bonding halting algorithm gives the right answer, the machine M can make the wrong guess for X and produce a wrong answer. But the point will be that for the correct guess, the reduction generates instances of bonding halting with very small entropy deficiency. And we actually need things to work only for the right guess of K. Okay. So here it's really important that we are working with a search problem, and that's why we had to spend some time in establishing this reduction. Like if you're trying to solve a search problem and there is no solution, no matter what you do, you will not find a solution. You cannot possibly make a mistake. If there is a solution, you can do all kinds of different things. If one of them lets you find the solution, you're doing well, kind of no matter what messy things happen in the other circumstances. So here, what are we doing? We're getting X. We're making a series of possible guesses for what is the probability of X. Some of these guesses will be wrong. And let us create instances of Bunny halting with unpredictable messy distributions. And we have no guarantee that our average case Bunny halting problem will solve them. So something on which we make no guarantee will happen in those cases. But one of the guesses is correct. For the correct guess, we are creating instances of Bunny halting with essentially nearly uniformity, just a constant number of bits of entropy deficiency. So then the Bunny halting problem will work on those instances, except with small probability. And kind of all the things that we just said means that we will find the witness. So kind of all things taken together, saying that if there's no witness, we find no witness. If there is a witness, we try lots of things, and at least one of them will succeed in finding it. And that's good enough. Okay. So if you were to instantiate it to any sampleable problem of interest, what will be happening here? Like say, imagine planting click. You get a graph. Maybe in that case, you don't even need to guess, but let's say you guess what is the probability that the graph would be generated according to the distribution. So you, for each of those guesses, you pick these functions h and g. You compute a hash of the graph down to log of the inverse probability of the graph. And that will be the Bunny halting instance that you construct. The machine M with this code, the hash function h, the hash of the graph, the hash function g. And what is M going to do? We'll try to guess a randomness for a generation. So the original edges of the G1/2 random graph and the choice of the subset. That would create what we're seeing. We check these hashes, and if everything checks, so it proceeds that way. At that point, actually, there is nothing more to do because the randomness of the sampler is already telling you what is the click. For a generic problem, the randomness of the sampler actually is not giving you the solution, so you will continue with a non-deterministic computation that will also find a solution. Any questions or discussions? So then, if not, I want to argue why this is sort of the end of the line for generality. As some we said, take any problem in NP, any distribution D that is sampleable, and now PD will reduce to our complete problem. But what about, for example, any problem in NP and any distribution at all? Could we hope for a reduction like that? So this would sort of mean that wooden average algorithm for a specific problem would be enough to solve any problem in NP under any possible distribution. We don't even need to worry whether the distribution has an efficient sampler or not. Well, somehow if P is equal to NP, in a way, sometimes this is possible simply because any problem would have an efficient algorithm, worst case. So certainly it would also be an efficient algorithm under any distribution. Actually, that's it. So to show you that there is a distribution. We call it D sub S. Such that if a problem is efficiently solvable on average, and this could be Levin's definition, Impagliazzo's definition, a definition that Sam was suggesting yesterday, then P is worst case polynomial time.
S depends on P?
No, actually it doesn't even depend on P.
It sort of doesn't type check for me. It sort of doesn't type check. So DS is a distribution on instances.
Yeah, I mean, let's think about problems for which any Boolean string is a possible input. If it's wrongly formatted, it's just a no input. So yes, it's a distribution that produces binary strings that can be interpreted as being encodings of any particular problem, so that for every possible problem, if the instances produced by those distributions are efficiently solvable on average, you can actually solve the problem in the worst case.
Sorry, Luca, why is that not a trivial statement unless you assume something about the distribution? Distribution is singleton on one instance, then the worst case and average case is the same thing, no?
No, because look at the quantifiers. There's just one distribution. I'm saying that take any problem that you're interested in. If the problem is polynomial time solvable on this distribution, then it's also worst case solvable. If your distribution is a singleton, you're telling me, well, if your problem is, what does it even mean to be efficiently solvable on a singleton? Kind of what problems are efficiently solvable on a singleton? It doesn't imply that they're solvable in the worst case.
But the algorithm can depend on the distribution. You could have a separate algorithm for each singleton.
Okay, but I could have a distribution which for every size, for every n, there is a singleton. So you're not going to have one algorithm for one instance. You still have to have one algorithm for a sequence of instances, but the distribution is very degenerate. For each n, it's. I know I'm asking something down here.
So again, like maybe you will answer, but yeah, the start checking is interesting because suppose the problem is such that if the unless the prefix of the first n/2 bits is very particular string, sorry, the digits of pi, then the problem is trivial. Then it seems like the probability that you find a non-trivial input under DS would be exponentially small, no?
No, that's the amazing thing. So let's. Thank you for this example, because that really shows why it's a surprising fact.
Can you repeat the example? One of the two of you?
What's that?
Boaz, can you repeat the example?
Oh, sure. Maybe Luca can
Yeah, or
explain.
can you explain can you repeat the example? I just didn't catch the example.
So Buzz was saying, imagine there's some problem where if the first half of the string is not all zeros, the answer is yes. And so if there are difficult instances in this problem, it's only instances where the first n/2 bits are all zeros. So now my distribution it means that my distribution must be concentrated on strings where the first n/2 bits are 0. But what if I have some other problem where the strings where the last n/2 bits, if they're not 0, everything is trivial, and it's only the first one that have to be 0. So now my distribution is kind of concentrated on strings where the last n/2 bits are 0. So what is going on? My kind of distribution is 0 everywhere. So there is something kind of strange happening, and the proof needs to navigate against this kind of counterexamples. All right, so let me describe the distribution. It will be a really highly non-sampleable distribution. So this theorem will not help us find a worst case to average case reduction. So this is I'm not sure what is the most common spelling, but it's something like this: solo none of universal prior. And it's a distribution where let's say on strings of length n, so each x has a probability that is proportional to 1/2 to the Kolmogorov complexity of x. So let's, I don't know if everybody knows what we mean by Kolmogorov complexity of a string, but k of x is the minimum length of a pair MZ, where M is a program such that M of Z is X. So the concept of Kolmogorov complexity is to think about a very generic form of data compression, where you allow any possible algorithm to do the decompression. And basically, among the possible ways of compressing X, you're really allowing any possible compression, decompression algorithm, but you have to provide the code of the decompressor as part of the encoding. So it has to be some kind of self-extracting compression. So a possible compression of X, it's any way of writing down some code and then providing some input for the program such that if you run that input on that code, you get back X. There are sort of infinitely many ways of doing that. Some of them will be short as possible. The shortest meaning how many bits it takes to write down M followed by Z. Whichever way is the shortest possible, that's defined as the Kolmogorov complexity of X. So the precise definition depends exactly how you write encodings of programs or of Turing machines. But as long as you have a compiler that changes one type of encoding to another, these different conventions change only by the length of this compiler, which you could kind of add to what you're writing down. So normally just say fix some encoding of Turing machines that you want, and that will be the definition. If you chose another one, there would just be some absolute constant that makes a difference. All right, so it's called Kolmogorov complexity because Kolmogorov studied it. Solomonov had some super general theory of how to do inductive inference, also extract knowledge from a time series of data. And it was a kind of Bayesian approach where the prior was this distribution, where strings that have short descriptions are more probable, and strings that have long descriptions are less probable. It was a kind of Occam's razor kind of thing, where you prefer shorter explanations for what you see. Be that as it may, that's a distribution over strings, and it's well defined. Here I'm saying probability is proportional to that. In fact, these inverses of Kolmogorov complexity, they add up to 1. So the factor of proportionality, it's less than 1. Or you could define it as a probability distribution even over all possible strings. If you do it just for some particular n, the factor of proportionality, the factor of proportionality is more than 1. So the actual probability of an X, it's a little bit more than 1 over 2 to the Kolmogorov complexity of X. All right, so my claim is that if you're looking at some algorithm that performs well under this distribution for some problem, actually the only way this can happen is that it performs well on all inputs except possibly finitely many. So here is the claim. All right, so the crux of the argument is that if an algorithm that performs well on average on some problem under this distribution, the only way this can actually happen is that it performs well, like it's correct on all but finitely many inputs. So it means you can convert it to a worst case algorithm just by fixing those finitely many inputs on which it's incorrect.
So you don't even have to change the algorithm. It's the same algorithm that works.
It's essentially the same. The same algorithm is correct, except on finitely many inputs. If you fix those inputs, then you actually get an algorithm that is correct on all inputs. Was that the question?
Yeah.
Yeah, that's how it works. All right. So to see how this works, so this relies on the fact that Kolmogorov complexity is undecidable in a super strong way. Like, not only you cannot compute the Kolmogorov complexity of a string in general, but you cannot even approximate it. In fact, for any sufficiently in fact, the following thing is impossible. So it's not difficult to prove that, in fact, that's sort of a way totally different from Turing's way of proving that there are unsolvable algorithmic problems. It is, so here is an algorithmic problem that is unsolvable, no matter how running time. It's just unsolvable in the undecidability sense. There is no algorithm at all. Say that I give you an integer k, and I want you to find a string whose Kolmogorov complexity is at least k. So for that problem, it's impossible to find an algorithm. This problem always has a solution, because by the way I define things, there can be at most 2 to the k strings whose Kolmogorov complexity is k, because they have to have different optimal encodings, and there are only 2 to the k encodings of length k. So there are only 2 to the k strings that have Kolmogorov complexity at most k. If you just, since there are infinitely many possible strings, there have to be infinitely many strings whose Kolmogorov complexity is more than k. So this problem always has solutions, but it cannot have an algorithmic solution. And this claim is that, so we will use this claim by showing that if there was a counterexample to what I said before, like if there was some problem that has a good on average algorithm under the Solomonov distribution without being good in the worst case sense, then we could use that to solve this problem that I marked in red of finding strings of arbitrarily large Kolmogorov complexity. So that's how the two things are related. So let me prove the statement in red. Suppose there was such an algorithm. no, let's call it C, because it will take us to a contradiction. Let L be the number of bits of the code of C, the number of bits it takes to write down the code of C. Well, now consider the string that is the output of C given K. Well, the Kolmogorov complexity of this string is at least K, because that's what it means for our algorithm to solve the problem in red. But the Kolmogorov complexity of this string is also at most L plus log K. Because if I tell you C, which takes L bits, and I tell you K that takes log K bits, I've told you what is the string CK. So K needs to be smaller than log K, and this is the contradiction. For sufficiently large K, this takes you to a contradiction. Okay. So no algorithm can construct strings of arbitrarily large Kolmogorov complexity. In fact, in particular, it really cannot construct strings of Kolmogorov complexity much bigger than whatever it takes to write the algorithm itself. Basically, the best you can do is to hardwire the string into the algorithm, and that's it. Right. So now I want to say that everybody's happy with the proof of the claim in the red box.
Yes.
Yeah. Now this is sort of undecidability results always relate to some kind of paradox. Here the paradox are things like what is the smallest number that cannot be described by 1,000 words in English? You think about that, it's problematic. So somehow here you're now I want to say that the statement in the red box implies the claim. So let's order equivalently that if I have some computational problem and some algorithm, my algorithm is working well under the Solomonov distribution, but it makes mistakes infinitely often, I can contradict the red box. So that's my proof by contradiction.
So Luca?
Yeah?
I guess, I guess the red box is interesting on its own, but you probably can just directly say that, say, the lexicographically first input of length and on which the algorithm fails. That's a short description, right?
Exactly. That's well, not even let's. Yes. Okay, so let's collect our pieces. We have a decidable problem P. We have an algorithm A. A fails with probability less than 1/poly, and I don't remember what exponent works. Let's make it, I think 1/n is fine. Let's make it n cubed on ds. Now, the fact that A fails with probability that is inverse polynomial, and by the way the distribution works, this is saying that if A fails on an input X of length n, then the probability of that X needs to be less than 1 over n cubed. Otherwise, that X itself accounts for all the failures that we are allowing for that algorithm. So the probability under dsn of X needs to be smaller than 1 over n cubed. And the probability, okay, so that means that the okay, so I didn't compute that factor of proportionality, but that one was between 1 and n squared, so that's why it was this n cubed. So something like this holds. So this means k of x is more than log n. And now if there are infinitely many inputs on which the algorithm fails, well, we can generate strings of arbitrarily big Kolmogorov complexity, because every string on which the algorithm fails has Kolmogorov complexity at least log of its length. So, you know, someone gives us a value k, but we're just going to look at inputs of length 2 to the k or more and keep looking until we find an input on which the algorithm fails. If there are infinitely many, there has to be some. We find it and we output it, and we get the contradiction. So notice that we just need A to be an algorithm and the problem to be decidable. Didn't need the algorithm to be polynomial, didn't need the problem to be in NP. And so this argument always works. So if you look at it in the contrapositive, if a problem is worst case hard, this distribution always hits hard instances. So no matter what they are, this algorithm will, not this algorithm, this distribution will always find them. Why it will find them? Well, because somehow if the algorithm fails anywhere, there is an algorithm for finding those failures. And so those failing instances have a short description, and so they have a high probability. So there is also a way of thinking about where this probability is coming from. It doesn't exactly describe a way to sample it, but it's pretty close. So you can imagine that you're going to generate a stream of random bits until you get something that looks like a pair like this, like some prefix-free encoding of a program followed by a prefix-free encoding of some string Z. Once you do that, you run the program on that string, and then you output what you get. If the program doesn't halt, that's sort of a failure of the sampling, you restart the sampling. I mean, it's not a sampler because it's doing undecidable things, but a way to think of what this distribution looks like, it's sort of pick a random program, pick a random input, see what it does, output that. And so if you have any problem at all and any algorithm doesn't always work, you will find inputs on which the program doesn't work simply by generating the program that looks for that, so which has a kind of constant size. This is a little more than a curiosity, but I think it's an interesting point that when we're looking for a more and more general version of Levin's result of about the completeness of problems, things cannot become arbitrarily general. Somehow samplable distributions, it's about where you might want to stop.
Okay, if you allow the algorithm to be randomized, does this work?
I couldn't hear the question. There was, I guess it wasn't close enough to a microphone.
If the algorithm is randomized, does this work?
Yes, if the algorithm is randomized, you can still make it work. Because still, if we are talking about randomized algorithms, there is some notion of kind of good inputs and bad inputs. So if the randomized algorithm works, what it means to work on a certain input, it's that on that input, it works on at least 2/3 of the random strings. So then you could take that as your definition of working is still decidable, so the argument still goes through. Yeah, so I guess it's actually about time to wrap up. So I'll get to really what we don't know how to do with this theory. Really, what are the open problems? I've been there for 37 years and are still open. So one is the difficulty of get natural problems to fit into this style of reductions. And here, when we talk about a distributional problem, there's always a problem and a distribution of instances. And so you can always say we're thinking about 3SAT. I can take Bonding-Halting under the uniform distribution. I know that Bonding-Halting reduces to 3SAT. So I'll just look at that reduction. And now that's actually a good average case reduction for the distribution of 3SAT instances that I get by applying Cook's theorem to Bonding-Halting. So kind of any NP-complete problem is also NP-complete in Levin's sense with respect to some weird distribution, which is whatever distribution I get by starting from Bonding-Halting and then applying Cook's theorem or kind of whatever reduction exists from Bonding-Halting to the problem. But then I get a not very interesting distributional problem where the computational problem is interesting, but the distribution is weird. We saw that you can take a not particularly interesting problem like Bonding-Halting and get it hard under the uniform distribution, which is really nice distribution. Somehow what's missing is to get an interesting problem under an interesting distribution to form a distributional problem that we can fit into the theory. So things like mean bisection in the stochastic block model or planted independent set in sparse graphs rank one, extracting a rank one tensor from a spike tensor plus a random tensor. Like, none of those things seem to fit into this theory. And in my opinion, the reason why this seems to be so hard is that when we do a reduction, we, in this framework, we are working with problems where a constant size piece of the problem is able to encode any program. And so, so that's why they are NP hard. The problems like independent set, SAT, and so on, they're NP hard because polynomial sized pieces of the input can encode a circuit. And that's sort of a really different thing. And it seems that for problems like bunny halting, we can get completeness by fixing a tiny piece of the instance to be sort of the critical part that encodes most of the reduction, and then all the rest can be random. But when you're working with SAT, you cannot really get a constant size piece of your SAT instance to encode what problem you're using from, and the rest to be random. So I feel like this is the missing piece. I don't know how to formalize it, but it feels like it's just not possible to fit problems like SAT and the uniform distribution into this framework of completeness. However, even a weaker goal still seems pretty difficult, although it might be achievable, which is to sort of forget about the kind of top level goal of proving the problems are complete. Just show the problems are related. Like say in fine-grained complexity, the goal is not to show that a problem like diameter is complete for time n cubed. That would sort of be too extreme to hope for. If it was true, then even by the time hierarchy theorem, we would know that it takes time n cubed. But it's too much to look for. What we have, it's more like little networks of reductions that show that seemingly very different problems are related. So I'll be here because well, maybe one can reduce mean best action in a stochastic block model to planted independent set in sparse graphs. So it's more sparse graph, both problems seem to require exponential time and stuff. But we don't have reductions of this form. And in fact, even tiny challenges seem to be really difficult. Things like reducing, refuting, 4-SAT to refuting 3-SAT. Random. Give you a random 4-SAT instance, I want you to refute. Can you somehow reduce it to refuting a random 3-SAT instance?
So look, I'm curious, this is Guy. So certainly some problems are super challenging to reduce amongst each other, but there are a bunch of problems that are reducible from planted cleat. Like especially, you know, these planted problems studied in statistics. So sort of curious, like how you feel that fits in.
Well, yes, I mean, in fact, the whole point of this program is that some reductions are possible, but it's so strange that kind of how fragile things are. Somehow reducing 4-SAT to 3-SAT seems so basic, but in the random setting we don't have reductions. Taking different graph problems also seems hard to do. Definitely, there are simple problems that you can reduce to more structured ones once you discover that kind of the simple one is really the underlying difficulty of the other. But say, but I feel like a lot is still missing. That like things that should be doable, we don't have the techniques to do them, and maybe by the end of the program we will. But
Yeah, I'll agree with that happily.
Maybe also, this is a question maybe for Guy. These reductions in statistical problems, are they usually bidirectional, or are they usually just in one direction? So you can start with somehow a harder problem and reduce to an easier, but unlike NP completeness, unless the reduction is identity, maybe you typically don't know how to reduce in the other direction, or?
Yeah, so Buzz is asking about bidirectional reductions for statistical problems. Yeah, so far, I'd say that there are bidirectional ones, but they're all in the pretty trivial setting. And indeed, I think that's one of the most interesting questions, is to get equivalence classes of problems in both directions. So starting from Planck Clique, it's almost the easiest problem that you might think about. And assuming that that's hard, it's relatively easier to reduce to other problems that have more interesting forms of noise and things like this. Good question.
But they're not equivalent, right? So you can
Certainly
say some kind of matrix decomposition problem is hard if Planck Clique is hard, but not vice versa.
That's right. That's right.
Yeah, and then particularly for refutation problems, reduction seems to be really difficult to think about. That somehow when you're trying to construct something, you can argue, well, I get a solution from this, then I get it from there, or somehow I try several things, provided that one of them works, I get it back. But some of the refutation problem seems even trickier than search problems to reduce to one another. And then finally, but that's kind of less of a concern for this program, it's that in from all the ideas originated from Levin's work and subsequent ones and so on, there's very often this idea of kind of putting somewhere in the instance you construct the code of the program, of some program. And kind of when you really go and see what is costing you, it's costing time or success probability that is exponential in the length of this code. So thinking about problems that have a non-trivial definition, this code is sort of the definition of the problem, something that checks whether a solution is valid or not. For problems that have fairly kind of complicated definition of what is a valid solution, something exponential in the length of the code of that, it's just a gigantic dependence. And but really all the basic results use this. And actually even in the paper that in some sense you cannot avoid it, but kind of the paper had loopholes. So that's another issue that for the sake of the general theory, I think should be addressed. Okay, I guess that's all I had time for. Thank you very much for your attention despite all the difficulties of listening remotely.
Let's thank Luca. Yeah, run the mic around to you if you put up your hand.
Luca, okay, bounded halting problem is an unnatural problem on unnatural distribution, which is strongly believed to be hard because of its completeness property. Is there some unconditional evidence of its hardness, like maybe sum of squares hierarchy? Is it, I don't know if it's possible to formulate even this question on this class of unnatural problem, but was there any attempt to give some other evidence of hardness of this problem, or bounded circuit complexity, or something like that?
Well, because of the completeness, what is happening is that if this problem is tractable, then every problem in NP under any sampleable distribution is also tractable. So any sum of square, for example, evidence of intractability applies to a problem that is as a sample distribution of inputs and it's itself in NP, is also kind of implies evidence for the intractability of Banach-Halting under the uniform.
Okay, yeah, that's a good point. I missed that. But is there some even stronger, perhaps, evidence of hardness which we don't have currently for other more natural problems?
No, basically, the question of the hardness of Banach-Halting is literally the same as the question of the average case hardness of NP with respect to sampleable distribution of inputs. So let's say in the worst case setting, what evidence do we have that P is different from NP? Well, we have specific algorithms or classes of algorithms that we can show that they don't work. So in the average case setting, I would say the strongest evidence is similar, that for various problems, we have classes of algorithms that we can show that they don't work.
Maybe one piece of evidence maybe for bounded halting that say planted click or Randos reset doesn't have is that because everything reduces to it, then also breaking crypto reduces to it. So
yeah, certainly we have 60 years of attempts at breaking crypto, and that's right.
Okay, so there is some even stronger evidence that cloud.
Yeah. So in fact, that's I should have mentioned that. That's one of the corollary of that reduction of search to decision, because of pretty much any cryptographic problem is breakable if you can invert one-way functions. So given f of x, where f is an efficiently computable function, you can come up with a pre-image. But that's, as defined, an NP search problem under a sampleable distribution. F of x, where random x is sampleable, f itself is the sampler. The problem is in NP. And so if Banach-Halting is, as a decision problem, is solvable under uniform distribution, then all one-way functions can be efficiently inverted, so kind of all cryptography can be broken.
Other questions for Luca? Okay, let's thank Luca again for all wonderful series of 4 lectures. Great to see you, Luca.
Same.
And we'll be back at 2.